the NIST goal is, well, it is on the perimeter level, right? Even though like modularity and composability is important, even though system level security is important, it's not necessarily the goal of this effort right now, right? Modularity, composability is important. Testability is very important, ease of testing. And this ease of testing is both pre and post silicon level that we touched. We discussed a little bit the attacker's capability and whatnot. And it was emphasized that the usability of what comes out of this effort is very important for this, right? I think as the whole community at the moment, we agree that there is a need for different security levels, right? And even though there are like well-established models for such an attack security, the models for fault maybe is not as established as such, so there is still room for improvement there. And we also discussed that, well, latency is still a challenge. So today we will have, again, two parts, right? On the one hand, there will be presentations on verification methodology, verification tools. And we will also continue with a panel discussion. And during the panel discussion, I'm hoping that we will tackle more deeply some of the open issues that we left yesterday, such as the randomness, what kind of randomness, and other things like, for example, the order security, level of security, and those kind of things, right? With that, I think we can go with the first presentation. It's going to be given by David, that is on silver leakage verification. So I will turn off I will stop sharing so that David, you can share.
Yeah, thanks, Birgit. Can you all hear me?
Yes, we can.
Okay, so let me share my screen. Unfortunately, my video is not working. So, yeah, can you see my screen, my presentation?
Yes.
Okay. So, yeah, thank you for giving me the opportunity to talk our recently developed tool, which is called Silver and is for formal verification of master implementation. And yeah, this is the result of a work we did together at the Ruhr University, Pascal, Amir, and me. Yeah. So yeah, the current situation is that recently there were several security notions published for master implementations, and also at the same time a lot of tools for verification were published here. And one tool to mention here with a wide range is MaskVerif, which is a language-based tool. So it works on kind of a defined language. And yeah, this has the advantage that it is fast, but these language-based tools come with a disadvantage that they are not in direct conformity with the security notions. So for some designs, they decide over conservatively, which means that, for example, for deep probing security, MaskVerif or a language-based tool says, okay, our design is unsecure, but if you regard the security notion and the statistical independence, for example, actually the design is secure, and this leads to overhead introduced by the designer, or can lead to overhead introduced. Yeah, and our goal now was to build a tool which is sound and complete, which means sound means that it is in direct conformity of the security notions, and complete here means that it basically supports all the established security notions. First, let me clarify some fundamentals we need to understand how to understand how the tool works. And the tool is based on so-called ROBDDs, which stands for reduced ordered binary decision diagrams. and it's basically a graph, or can be seen as a graph representing a Boolean function with binary output. And the nodes are the inputs, and the leaves of the graph or of the tree are the possible outputs. And each of the nodes can be seen as a root of a subtree which defines again a function. And the function is then defined recursively. For example, if we consider the node x2 here, if x2 is 0, the function would output 1. If the node is 1, it would output 0. If we go farther to the x3 on the left-hand side, the node describes the function which says, okay, if x3 is 0, we will output 1, and if x3 is 1, we will output the result of the function defined by the node x2, and so on. So we can define a Boolean function or represent a Boolean function. And all that means that if you go from the root to a leaf, you will traverse on the path every node or every input in the same order. And reduced means that there are no isomorphic subtrees and also no redundant nodes. So basically this is kind of a minimal representation of a Boolean function. And what is quite handy is that this is a well-examined topic to using ROBDs to determine the distribution at the output. Yeah, so determine the probability. Basically, if we say the input variables are independently and identically distributed, the output, it's basically a counting problem. Yeah? So we count how many runs, for how many inputs the function is 1, and for how many inputs the function is 0. And this can be efficiently done with this structure. Yeah. And how do we use this in the formal verification? We have our circuit, yeah, so digital circuit, and each of the wire represents or can be seen as binary random variables, yeah, and function of the input. For example, Q1 is a function of the input variable x1 and x2 is a function of x2 and x3, and Q3 is a function of all the input variables. And yeah, these functions can be presented using the ROBDs, and especially what is handy for the formal verification is that we efficiently can compute the distribution over these wires, basically. And this is what we use in our tool. Yeah, and then let me quickly recap statistical independence. Yeah, so 2 events are said to be statistically independent if exactly this equation holds. So if the probability that both events occur at the same time is the product of the probability that the events occur separately or individually. And then we can extend this definition to random variables. 2 random variables, x and y, are said to be statistically independent if for each value combination they can take. So for if x, the random variable takes value x and the random variable y takes y, is an independent event for every value combination, basically. And this, as we are interested in our case, in the bias and observation of the circuit, we are interested in binary variables. And then it gets easier. We don't have to make the check for every combination, but one can show that it is enough to do it for one combination. Yeah? So basically, to say that both binary random variables x and y are statistically independent, we can simply show that the event that x takes 1 and y takes 1 is statistically independent. And the intuition behind that is simply that for a binary random variable, the counter event of x equals 1 is x equals 0, and the dependency is defined symmetrically, right? So if x is independent of y, also y is independent of x. And so you can show that this is enough for binary random variables. Yeah, so we have to make only one check again of 4. And then we extended this approach. So we showed that basically for joint distributions over binary random variables. So now we consider two sets of binary random variables, x and y. And to show that the joint distribution over these sets are statistically independent, one can show for every subset that the values in the one subset or the random variables in the one subset are equal to 1 is statistically independent of the event that the random variables in the other set, for example, y, are equal to 1. And this for every subset. Yeah? So I made an example here. We have two sets of random variables, each containing two random variables. And then basically we have to check for each of the subsets here, whether they are statistically independent if they all take the value 1. Yeah? And this results in checking 9 of these equations, basically. Yeah, and that these sets are all, or that the values in the sets are all equal to 1 is also kind of that we want that we reduced to checking that, and we reduced that to checking sets where all of the random variables are set to 1 is kind of handy, because now basically the event that all the random variables in the set take 1 as a value is equal to saying that the logical conjunction of these random variables are equal to 1. And the logical conjunction of these random variables are again a simple binary random variable. Yeah? So what we did is we reduced the independence check of joint distribution over sets of random variables to several checks over simple binary random variables. And again, this is a combination of binary function, basically, in our circuit again, and this can be efficiently done using the ROBDDs. Yeah, and then our approach was to redefine all the common security notion with respect to statistical independence. And yeah, this is heavily related to the paper by Lauren de Meyer, consolidating security notions. And yeah, basically redefined all of these notions with respect to statistical independence and of joint distribution over random variables. And then we did this check, as I mentioned before, using the BDDs. Yeah, and as an example, we can take the deep-probing security symbol. This is already defined as statistical independence. There we have that each probe on the circuit must be independent of the secret input. Yeah? And in the case of first order, we only have one random variable, so one probe, and each of these variables has to be independent of the input. For example, here, if we have 3 unshared input variables, Q has to be independent of the joint distribution over this random variable. And again, this is simply checking whether Q is statistically independent of the joint distribution over the input. And we can do this efficiently doing the using the ROBDDs. Yeah, and then we have the non-interference as a security notion, and all this, and also strong non-interference and probing isolating non-interference. They are all based on the simulation argument. So for each probe on the circuit, you should be able to simulate it perfectly by using only a subset of all shares, input shares. And this subset, depending on the security notion, has different constraints. Yeah, for example, if we consider first order non-interference, if we have one probe on the circuit, it must be for each probe, there must be a set which contains at maximum 1 share per input, must be perfectly simulatable with that. And for strong interference, there are higher constraints. So if you probe an output, you must be able to simulate it without any input share. And for example, for probe isolating non-interference, it is about the circuit share. So if you probe at the output at a certain index of the output, the simulation set should only contain shares with the same index, which corresponds here to the circuit shares. Yeah, and basically we can then rewrite this as probabilities here. Yeah, this is simply the distribution over the probes given the simulation set should be equal to the distribution if we only know the distribution over the simulation set only given the over the probes only given the simulation set should be equal to the distribution of the probes if given all of the input shares. And if we assume that all of the input shares are identically and independently distributed, this simplifies to checking the independence of the joint distribution over the probes and the simulation set and all shares that are not in the simulation set. And again, now we reduced it to a comparison of joint distribution. So determine the statistical independence of these two distributions. And this can be again done efficiently using BDDs. Yeah, and extending this to glitch extended probes, so to hardware, is rather simple because this is only a pre-processing step, right? If we have, for example, two registers and in the middle of it, in between, we have several logic functions, and we probe here, for example, Q3. Now, for deprobing security, we have to show that Q3 is independent of the unshared input. But in the extended probes, we have to go back to the last synchronization point, which is that register here, and have to show that Q1 and Q2, everything that goes into the computation of Q3, are independent of the secret input. Yeah? So basically, the standard probe was Q3, and then in the extended model for hardware, now it's Q1 and Q3. And then again, it's basically checking joint distribution, right? We're just doing a pre-processing step here. Yeah, and we also support checking uniformity at the output. And here is given, which is crucial for composability, especially in TI scenarios. And yeah, as an example here, we have 3 output shares in the shared circuit. And we showed that instead of checking this property here, we can also check that each tuple or each combination of 2 of the output shares are jointly balanced here. Yeah? So to show that the output is in uniform, we can instead show that all pairs of outputs are jointly balanced. Yeah? So it's equivalent to do that. And yeah, we show in the paper that we generalize this approach even for higher number of shares and even for multiple shared outputs. Yeah, here we have only one shared unshared output, so only Z, but we also show that we can do it for multiple unshared outputs. Yeah, and how does our ROBDs help us here? Basically, if you have a set of random variables or outputs, you can show that the joint distribution over this or that the set is balanced if each component function is balanced. And component function is simply the all of the linear combination of the random variables in the set. And again, the linear combination of the random variables in the set is simply a binary random variable. So we can do this again by using our BDDs here. Yeah, and we support several security notions. So we support deprobing security, D-non-interference, D-strong non-interference, deprobe isolating non-interference, and also the output uniformity. Yeah? And for the security notions, we support them in the standard model, which is relevant or mostly relevant in the software scenario, and also the glitch extended model, which is highly relevant in hardware. Yeah. And then let me give you an overview of the basic program flow of Silver. So we can either give Silver a Verilog file, then it will be passed by parser to a netlist. This netlist is in a self-defined format. we can also just, because it's easy understandable, just write the netlist for small examples. And then the netlist is given to the actual analyzer, which is based on the statistical independence checks using the ROBDDs, and then it outputs the result. And the result in our case consists of the security order of the design for the corresponding to the security notions, but also for the first failing probe for the order it does not fulfill. And this is kind of handy. If you want to gain higher order resistance, and the tool says, okay, at this point or with this probe, the check fails, then you can, at this point, introduce, for example, a register, or you can introduce randomness. And this is kind of handy, this information. Yeah, and we basically ran Silver over several designs, several gadgets which were published, which can be seen here. And D is basically, D+1 indicates the number of shares basically. And the tick behind this check symbol is always the security order, which is fulfilled, or if it's not fulfilled, it's marked by this cross mark here. And we also did this for several S boxes, as you can see here. And yeah, I think it's a quite nice overview. And also for some affine function. And yeah, the quadratic bijection 412, we also inserted here. Yeah, and let me quickly discuss the advantage of being sound. Yeah? So we are avoiding completely false negatives. So if we say the design is unsecure, with respect to a security notion, it is unsecure. For example, let's take the design from the paper Consolidating Masking Schemes here, and which is a shared realization of Q412. And here, language-based approaches tend, for example, like Masquerade, tend to categorize it as unsecure. But if you consider the deprobing security, it is actually secure, and our tool verifies that. So what a designer will do is basically adding additional randomness. Yeah? Because now the tool reports that it is secure, but this randomness is from the beginning not necessary. So you unnecessarily introduced overhead into the design. And for larger designs, this can get bigger and bigger. So it's actually a good property to be sound to the actual security notion. Yeah, and as I said, so Silver is complete. It supports mostly all of the established security and composability notions. We have the soundness to avoid introducing overhead into the designs if we are a designer, because we are in direct conformity with the statistical properties and the security notions. Yeah, and we also return the failing probe. As I said, this comes also in handy. So for higher order masking or for easier fix of mask designs, we can introduce additional randomness and yeah, things like that. And one disadvantage, of course, is that in comparison to language-based design, language-based tools like Masquerade, we are slower, right? Because we are actually comparing distributions here. Yeah. So let me give you a quick demo of the tool. If you clone it from Git simply, you already will get some test files, so test folder with several design files. And let's take, for example, hardware private circuits and test one of the designs. So yeah, so we can just define the device under test here, which is already an HPC run. It should be secured up to the second order, so it uses 3 shares. So this is what we check, and this is basically, now I'm already giving the tool the netlist, but you can also give them a Verilog file, and then it will convert it or pass it into a netlist. run this. Okay. And let's check the design. And then you get this overview and see how much gates it has. And yeah, here you have an overview of the security notions. Yeah? So it's probing standard secure in the probing model up to the second order, also in the robust model up to the second order. It is non-interference up to the second order in both standard and robust model. SNI, it is up to the second order in the standard model, but it is not, even not for the first order in the robust model, and it directly returns the failing probe. Yeah? This is basically the line in the netlist, and then you can have a look which wire it is, and you can try to fix it. Yeah, and this design is also PNI in the standard and PNI in the robust model. And also the output uniformity is given. So I think it's a very nice overview. If you input a gadget, you will get a nice overview of all of the common security and composability notions. Okay, this was it for the demo. And as a conclusion, I would say with Silver, yeah, we developed an easy-to-use tool for sound, meaning that we are in direct conformity with the security notion, and also a complete tool in terms of we support all of the established security notions. Yeah, and yeah, this is basically a nice tool for the security and composability of master implementations. And here are some additional informations. So if you are interested, you can download the tool. It's on GitHub. Just clone it and play around with it. We are always happy to get feedback for the tool, so please try. And the scientific paper is on ePrint, so take a look there as well. Yeah, but I think the slides will be uploaded, so you can do it afterwards. And feel free to contact one of us if you have any questions or any other regards. Yeah, and this was it basically from my side. Thank you for your attention. And are there any questions?
Thank you. Thank you for your presentation. If there are...
Hello. May I ask a question?
Sure.
Hi, this is Luis from NIST. Actually, I have two questions. The first one might be fast, I think. You mentioned in the beginning of the presentation that you can efficiently compute the distribution of the wires. Is this claim conditioned on some sort of statistical independence on inputs, or was this just a general claim?
Yeah, I mean, it is. These are OBDDs, so efficiently wise, they heavily depend on the input dependencies. Yeah, so complexity for this check gets higher if you have more input dependency, meaning that you have more multiplication in your Boolean functions and things like that.
Right.
Then computing the distribution will get higher.
Right. So, but when you mentioned efficiently, did you mean something like polynomial on the number, I don't know, of gates or inputs?
Yeah, I can't give you some concrete complexity. So we are still developing the tool, also trying to make it more efficient, because for large designs, yeah, it comes to its limits, I would say.
Right.
So if you give there a complete masked higher order icebox or something from AES, so it will come to its limit, definitely. Okay. So this is something we try to reach.
Sorry, I didn't mean to interrupt. The reason for asking the question is it looks like this is essentially like as hard as solving the SAT problem, as in you have a circuit, you want to know if there's any input assignment that would lead to a 1 in the output. This would be a hard problem, but is computing the distribution of the wires, of the output wires, the same as that essentially?
I actually don't know whether this is related to the sub problem. I only know that these ROBDDs are commonly used for this approach, or for this problem, that you have these output distributions and can, in some term, efficiently determine the output distribution.
Okay. Okay. I guess I'll remain with this thought basically. So it seemed to me like it would probably be hard in a generic case to actually know the distribution. In any way, moving forward, a doubt that I have is like in this demo that you showed, where you're providing an input and then obtaining a result. What are the actionable aspects of the input? Is it like basically a Boolean circuit where besides the typical gate you have registers? Is that all that you need for the input, that graph, or do you actually use any other kind of information?
Yes, so basically, I mean, for security notions like PD, you also need like the index. So you have to annotate the index of the shares and things like that. But otherwise, okay, you either put in the Verilog file and the registers, and yeah, then the check is based on this. You can also define the netlist yourself.
Okay, so it's basically the Boolean gates plus the registers.
Yes, exactly.
Okay, great. Okay, thank you very much for the answers and for the presentation.
And if there are any other questions, I would like to carry them to the end of the session, if that is okay. I see that, Mathieu, you have a question, but somehow the end of the session is also okay.
Hi, everyone. Can you hear me?
Yes.
Yeah.
Do we have time? I didn't get it. Do we have time for one question?
Yeah, maybe let's do that. Let's
okay.
go ahead.
Okay. So thanks for the very nice talk, and I think it's a very nice approach for verification. I was wondering, would it scale to non-binary variable? So if you have a circuit on a wider finite field, let's say GF256, would your verification method also applied in such a context?
I think there are approaches to using these BDD instructions, which is kind of handy, I think. And there's a lot of research done in this area. And there's also an approach to use it not only for binary random variables, but for arbitrary random variables. So this is definitely something one could try. And we are actually currently looking into this. So extending this from binary random variables to variables with more categories. Yeah.
Okay, thank you.
May I give a comment here, Matthew?
Yes, sure. Hi.
Hi, Matthew. Just want to say that currently, if you just write your program, whatever, I mean, design, for example, a Verilog design or very VHDL, doesn't matter. Anything that you define, and then you synthesize it, and at the end you get the net list. And the net list is just made by the binary gates. And then you are able to still analyze these binary gates, I mean, the net list of the binary gates by this tool. Then it doesn't matter which, let's say, consideration you had when you designed the circuit. Either it's just binary or as any other in any other field.
Yeah, that's right. But you could want to verify some property at a higher level. You might be interested in validating.
Okay. You mean that whether we can try this at a higher level, not at the gate level?
Yes.
Okay. Yeah, this is not done yet. I mean, the current version just checks the binary level, and means that if you turn your circuit, which is at any level, turn it to the binary level, you're able to check it with this tool, but it doesn't do it at the higher level to be more efficient. No.
Yes.
Right.
Thank you. Then I will, if there are any other questions, we can continue at the end of the session. And for the second talk of this session, there will be a presentation from Victor. He will show up another verification tool, Vermi-Verfi, which is verification against both such and false.
Hello, everyone. Can you hear me?
Yes, we can.
Okay, I'll share my screen. Okay. So let me know if you can see my slides.
Yep, we can see them.
Okay. So hi, everyone. My name is Victor Arribas. Over a month ago, I finished my PhD at COSIC. And since then, I've joined Rambus, where I'm working at the Rotterdam office as a security engineer. My interest includes design and verification tools for side channel and fault resistant implementations. And today I'm going to present the work I did regarding these tools during my time at COSIC. And this is a joint work with Svetlana Nikova and Vincent Ryman from KU Leuven, and with Felix Wegener and Amir Moradi from Bochum. So protecting against physical attacks is a highly complex task for which we have defined several methodologies throughout these years. However, when we implement these methodologies or these techniques, it's very easy to get something wrong and fail to achieve the security that we desire. The failures can range from a very basic bug in our implementation to a more fundamental mistake, failing to capture the threats, the physical threats that we want to protect against. Thus, it's extremely important to have verification tools to help us doing these things correctly. Ideally, to get a finer testing, testing procedure, we would like to test our implementation throughout the whole design flow. And to do that, we need tools, suitable tools that can capture the threats, the physical threats that our implementation will face later on. As we have seen already, we have plenty of tools proposed in the literature, all of them very nice tools, and which I think we could classify according to these axes here. So we have more theoretical tools that work at the algorithmic level, and we have also more practical tools that work with the prototypes, etc. We have tools that are more suitable for small gadgets, or tools more suitable to analyze complete Cipher full implementations. All of them have their own advantages and disadvantages. So we are going to see some of them here. Theoretical tools, on the one hand, they are noise-free. So they're not affected by the noise, since usually, as I said, they work at the algorithmic level. On the other hand, practical tools are very sensitive to noise, and the security assessment is very depending on the level of noise. Theoretical tools are also technology independent for the same reason, since they work on the theoretical, on the algorithmic, at the algorithmic level. They don't need maybe a prototype, while practical techniques may need this prototype or the actual device to launch their experiments. With the downside, or we could say, from theoretical evaluations, is that we have to do quite some assumptions on the model. Since we work at a more abstract level, we rely on the model that we describe, that we define, for providing a good security assessment. If the model fails to describe the security, the threats, the physical threats that we face, then our verification will be useless as well. On the other hand, more practical evaluation methods do minimal or no assumptions on on the security models, and just they provide a security assessment from the implementation as is. Then we can have tools more suitable, as I said, for small gadgets or complete ciphers. The first tools have the advantage of providing an exhaustive security analysis. Since we have a small gadget, we can exhaust all possible scenarios, security scenarios, giving a more thorough verification assessment. On the other hand, tools suitable for more complete ciphers cannot give an exhaustive verification assessment, but can give a more comprehensive or more complete security assessment. And since we are not able to exhaust all possible scenarios, we usually rely on statistical methods to compensate for that. So I think all the tools are complementary, and to achieve a thorough verification, we need we need to use multiple of them throughout the whole design and implementation process. So now I'll talk about the tools that I developed during my time at COSIC. I developed two tools, one for side channel analysis and one for fault injection. Both tools have a similar framework. They receive a Verilog or VHDL module. They automate the synthesis to produce a netlist. So this is very similar to as we saw in the previous tool. We can also give simply the netlist. And then the tool parses this netlist to build a structural model of the circuit, internal model, from which all the tests will be launched later, or the evaluation will be performed. Finally, we provide a security assessment on the conditions tested. So these tools are built based on logic and fault simulators. They use objects, pins, and gates as objects to build this structural model of the circuits, from where we then will launch these additional security tests. So the first tool, Vermi, checks fundamentally the TI properties. So we check for non-completeness and we check for uniformity in both combinational and sequential circuits. I won't get into too much detail of how we do things because I want to spend some time on the demo. So I'll show how these things are tested in some examples. Then Verify is the second tool which we use for evaluating fault-resistant countermeasures. In Verify, we aim to provide a flexible tool that can adapt to any possible fault model, so that any designer can verify its implementation according to the fault model proposed. So in Verify, we proposed a way to encapsulate the already proposed fault models, and we add a new level of fault models, which we name gate output fault model and gate input fault model. So these models distinguish between a fault injected in the output only, or a fault injected in both the input or the output. This second fault model could be also seen as a wire fault model, which is finer than the previous one. When developing the tools, we performed some experiments on previous works implementations. With Vermi, we were able to find a non-completeness failure in a full parallel implementation of a protected Ketchak. Vermi evaluates the dependencies, the input dependencies of the outputs. So with the tree search, it gathers the input dependencies. So for this example in particular, the tool found that all two shares for this output variable were used to compute it. To validate the findings of the tool, we also manually computed the inverse of the equations from Ketchak. So for example, for this bit here, we see that all two shares of bit 304 are used to compute your outputs. So now I'm going to show you some examples. So we're going to analyze this particular case. So we have here a round-based implementation of Keccak. So this is not the full implementation, but only like the data path. We have for the full implementation only the data path, which covers all the permutations. So this is a two-share implementation using DOM protection. So we have our input, two-share inputs, and here we only take the combinational part. So we output the expanded 4 shares from the nonlinear layer. So we can either analyze side channel or for the analysis. Now we want side channel analysis. We have several options, divide our implementation in subcircuits, gather the input dependencies, non-completeness and uniformity. Now I will, for the sake of time, I'll focus on the security checks. So we want to check non-completeness. For now, we have up to third order non-completeness check available. And okay, we run first order here. Remember, this is a two-shared implementation tailored for first order security. But the way it is implemented, we already failed non-completeness. So we have some file that gives us some information. So this is this file. So for this file, we get that there is a complete output. So this output bit depends on all shares of this particular input bit here. Okay, so now we will do the same exercise, but with the full round, where we include the register at the output of the nonlinear layer and the compression layer, just to see how the tool treats the sequential circuits. So now the tool has identified sequential circuits. So to analyze the non-completeness, we split the full implementation into different subcircuits. So in this case, we can see 401 subcircuits. The 400 subcircuits correspond to the second layer, to the second stage, where we have 200 independent circuits for the 2 shares. So in total 400 for all the outputs. And then we have an extra subcircuit, which corresponds to the full first stage of the circuit, which is actually the same circuit as we tested before, right? So we're going to test also the same non-completeness in this case. And now we get that the tool tells us, okay, there is a non-completeness failure in this test. And we'll see, we can see a similar report here. Yeah, okay, I don't see why we don't get it now. But so we would have a similar report similar to this outputted. So now I'm going to check the same circuit, but the secure version. So the secure version now has a register in between linear layer and nonlinear layer. So usually to secure a DOM implementation, we need, one of the conditions is that we need independent inputs. And we saw that if you have linear operations before these nonlinear operations, it's often that these dependencies are broken. There is dependencies introduced in the linear layers. So then these glitches are propagated, and then this would fail, the security will harm the security of our design. And as we saw, we would fail the non-completeness. So fixing, putting a register in between linear layers and nonlinear layers, in this case suffices to secure the design. we stop the glitches from the linear layers. So we do the non-completeness. So now at this time, since we added a new register layer, we have some more sub-circuits created. And then if we analyze the non-completeness, first order, now we see that it fulfills non-completeness. We can also check the second order non-completeness, hoping that it will fail, since this is a first order scheme. So now it takes a bit more time because we have 400 sub-circuits. So the tool, what's doing is combining all possible two sub-circuits within the same stage, because we only do a univariate analysis, and then combines two outputs from all these combinations of sub-circuits and checks the combined input dependencies. So we can see certainly all the sub-circuits fail because this is a first order scheme, but we can see how it tells you which combinations of smaller sub-circuits fail. And then if we check the file, we can see that more finely the outputs. Now I want to check an additional experiment on how we compute this uniformity. So we evaluate threshold implementation from the Ketchak S-box. First with 3 shares, which was shown to be non-uniform in the literature. So now we run uniformity, and we get that it's not uniform, and that gives us a file something like this with some various output frequencies for some outputs, which give us something like this. Like we see several different frequencies for the different test vectors. Now, if we run the same experiment, but for the 4-share version, which was shown as uniform in the literature, we also would like to see for uniformity that it is uniform. Now it takes a bit more time because we simulate 2 to the 20 inputs. So 2 to the 20 test vectors for all possible cases. So indeed, the test that we do here for uniformity is only available for smaller gadgets, like a small S-box or an AND gate, a protected AND gate, for example. On the other hand, the non-completeness evaluation can be used for for a full cipher. Okay, so now we nicely see that we get uniformity in this case. Okay, so coming back to our presentation, now I'll talk about some experiments that we did with Verfi. We evaluated the combined countermeasure party, where we found some implementation and design flaws thanks to our tool. So party claimed full coverage against faults of Hamming weight up to 3. And with the tool, we were able to find faults with Hamming weight of Hamming weight 2 that bypass the error check. So if we look at, this is the data path of party. We have the regular data path and the parity data path. So with a single bit fault on both paths, making a total of 2 bit faults, we could bypass the error check. We were able to bypass this error check. The reason behind this is that at the design of the scheme, they didn't take into account the presence of fanouts at the outputs of a gate, for example, or fanouts in the circuit. So even if we inject a fault in the fault model that they claimed, these fanouts would propagate the single bit fault into 2 bit faults at the time of the check, making an invalid code word. We performed also some experiments on impeccable circuits. We first validated their security claims against the fault model proposed. So we did some experiments on several Midori implementations. Here we can see a Midori with a simple parity check for a 1-bit fault. So for these experiments, we confirmed the full coverage that was claimed in this paper. And then we did some further analysis to analyze the fault models proposed in Verfi. And then we subjected these implementations to a stronger attacker model, namely the gate input fault model that we proposed. Then with this fault model, with this stronger fault model, we could see that some errors were not detected, were bypassed the error check. The reason behind this is that Impeccable Circuits proposes some techniques to avoid this fan-out propagation at the output of a gate. So if we are in the gate output fault model, we are safe. But if we go to this stronger fault model, and if we were to inject a fault in the inputs, this fault is propagated, in this case, to 4-bit faults at the time of the check. So this is a common thing, for example, in cryptographic ciphers, because usually the S-box uses a nonlinear function, then a single input will be fed into multiple gates. So now I wanted to do a couple of experiments with this. First, with Verfi, we have to pre-process our circuits. So by pre-processing our circuit, we get some fault configuration files. We get first file for a hierarchical fault injection. This allows us to inject faults in hierarchical modules, and then a component-wise fault injection. This allows us for a much finer fault injection, which could be also used for exhaustive fault simulation, for example. For the sake of time, so I'll show the file, how it looks like. Well, I'll show a already prepared file that I have. So we can decide the number of fault simulations, the number of faults per fault injection, and the number of faults per cycle in every fault injection. We can decide if faulting the hierarchical module. So we can see, for example, an outround key instance here. We decide to fault this outround key instance, which means faulting all gates inside. This decides output or input gate fault model. In this case, we'll use the output gate fault model, and then we'll target in which cycle. Now, usually for DFA, we want to target the last rounds, right? So this takes 98 cycles. So we will target towards the end. And then we will use single event upset or a bit flip fault. And the advantage of this methodology, well, first I want to show you that, so similar to the picture, we also inject the fault in the parity instances. But the advantage of this and what we wanted to give to the tool like this flexibility is that in this case, for example, in party, the control data path wasn't protected. So now we can nicely decide that we don't want to inject any faults in the control instance, for example. So we run this example and we get an evaluation file. So this example takes 98 cycles and it's a full party implementation. So it takes some time to run 200 simulations. It's not just 1 second. So I bring you the output here. So the output is a fault evaluation summary. We give some inputs. We gave some input test vectors, and we reported detected faults, the ineffective faults, and the non-detected faults for all the inputs, and then an overall summary. So as we can see here, with only 2-bit faults, we could achieve already, we could find some faults non-detected, failing to achieve the full coverage claimed. So we can see, like, for every input, we provide the reference outputs and the faulty outputs for the particular fault injection. This allows us also to with the experiments from the with the results from the tool to directly launch a DFA attack, which is not automated in the tool, but it gives the tools for it. So now we can see the error that I was presenting in the slides. So we see the parity faults and the instance and the regular data path fault in a given gate. So you get the gate somewhere at the S-box, and the clock cycles are at which this fault was injected. Okay, so you have the different faulty outputs for the different inputs, and then yeah, so that's the result for that example. And then I want to show some examples of these meadery and impeccable circuits that we tested. So we are testing, so again, we generate this configuration file, which looks like this. Again, I have already prepared it beforehand in order to save some time. So in this case, we'll run 500 fold injections with a single fault because we only have a parity path now. We'll start, so we'll fault almost everything. The only things we don't fault are some elements that would mean just injecting a fault in the output, so which is certainly not useful for the attacker, and could harm the coverage report. So besides that, we inject a fault on everything, and again towards the end of the computation, now we have 14 cycles. Now we use the fault model, the output gate fault model, with a bit flip fault. So we'll run this experiment. Then we need to provide some simulation information, how many resets cycles, how many load cycles, if we want to provide input test vectors, or we just want the tool to run random test vectors. We can do that with this file, this one. And then we provide a fault configuration file. No, in the demo folder. Config faults. Okay. Now we want to run the fault analysis. We run some fault simulations for a given several input test vectors. Remember, we are running 500 simulations of this toy Cipher implementation. And then we got some new files. So the report file looks like this. As we saw before, we report all the faults, both detected and in this case ineffective. We didn't have any non-detected. So we can see that the full coverage is indeed 100% as claimed. Remember that this might not be exhaustive, but we have selected quite some faults, so this is quite close to exhaustive. Then we will now subject this implementation to the stronger attacker model. So now we enable this input gate fault model, and we run again the same simulation, fault simulation. Now we have added additional faults, so we take a bit longer time. And the result now is that we do find some non-detected faults for almost every input given. So now we see that the coverage is still pretty high, but it's not 100% as claimed as maybe we could expect. This was not claimed for this fault model because this is a stronger one. And we see that indeed every fault non-detected occurred at the input. And as I mentioned before, it occurred at the input of the S-box which is the nonlinear operation. Okay, so that concludes the demo. And I would like to do a final reflection on how would I approach the verification methodology. So I bring you here as like a typical design flow of an ASIC. We see that we have several verification stages which give a feedback to the RTL in order to cover all corner cases and have a fully functional core. Then I think we could place all our tools, we could sort all our tools, something like this, throughout this design flow. And we could have, like, for example, the tools that verify our proofs to be placed at the very beginning in the design specification, the tools checking the necessary or sufficient conditions for smaller gadgets or full implementations as the ones we saw now at this stage. Then we can have some tools at the floor plan level or place and route level, which can have more detailed simulated traces. We had a comment yesterday about this, where we could have a closer model, like a model closer to reality. And then finally, we can have our final test on the prototype or the final product. We certainly wouldn't like to find that we had a mistake in our proofs on the final test. We wouldn't like to go through all this process with a faulty implementation, right? So that can help us to prevent that. And finally, I want to conclude saying that we have multiple verification tools with advantages and disadvantages, but I think we should use several of them in synchrony to provide a thorough verification. It's very difficult for a designer to guarantee 100% that no problems will appear, or this is fully secure, right? So the more tools we use, the more warranties we'll have. And finally, securing at different stages can help us speed up the security, the validation process. Because if we find earlier stage mistakes, we don't need to go through the whole process. Finally, just say that we have to verify our implementations, otherwise it's highly possible that flaws will appear later. So that's all from my side. Thank you for your attention. I'll be happy to answer any question.
Okay, thank you, Victor, for the presentation. Are there any questions? Feel free to also write it into the chat that we are keeping an eye on. And while waiting for the questions, maybe I will ask something to actually bolster the tool design, right? We discussed yesterday about the importance of flexibility, right? And also different design methodologies. How flexible are these tools to kind of verify different design methodologies? For example, I'm asking for both silver and where we work, right? There is like multiplicative masking scheme, in addition to Boolean masking scheme, empty masking scheme, or for faults, we discussed, for example, like redundancy using, not to say error coding, or like complete redundancy of the whole block. Can we verify these also using these tools, such tools, or their extensions, for example?
Should I start?
Sure.
Yeah. So for example, the first tool that I presented towards side channel analysis, that one, it's more limited in the sense, it's a very specific check that we do. We also do the uniformity, but that's a bit more limited. And those checks are usually meant for TI implementations. But for example, the non-completeness property, we have seen that all or most, if not all, algorithmic countermeasures need this property. So our tool would serve for this property, for all these countermeasures. But maybe, for example, countermeasures at the gate level, which do not have this glitch propagation such as LMDPL, maybe this tool couldn't help there because we don't need to check non-completeness maybe. So in that sense, it's limited as far as the necessary property it's needed. I believe the fault tool is more comprehensive, and we designed it with that in mind. We designed it so that we could adapt to as much as fault models possible. So any possible implementation that it's generating a netlist could be tested in that way.
Okay, thank you. David, is there anything you want to add?
No, I think Silver is basically for side channel analysis and to verifying the masking schemes, different masking schemes. But yeah, as I already said, it has a wide variety of security notions it supports. So yeah, we do check basically every established security notions, and it's also composability. So yeah, this tool is quite generic, but not for fault analysis or fault injection analysis. It can only be used for masking and side channel resistance at the moment.
For example, in the examples, I think I didn't see a multiplicative masking or additive masking example, but it can, because the notions are actually generic, it can also be used.
Yeah, sure. That's the main approach, the main goal.
Okay. Any other questions from the audience? Okay. Otherwise, I don't see any comments or questions raised. I think we can go to a break. Thank you again for the presentations, for the demos.
Thank you.
And I suggest we come back, say 3:30 at 12:30. So we have a 10-minute break then.
Thank you.
Thank you.
Right at the time. Yeah, thanks everybody, and also the panelists accepted to participate. I just collected some questions and would like to not actually try to answer most of the questions or provide most of the questions. I would love to give this control to the panelists and also to the audience. I mean, in the former panel, we didn't have much interaction with the audience. I would love to ask the audience if they have any question. Of course, they can easily unmute themselves and raise their hand and ask a question. But to start and warm up this discussion, I just collected a couple of questions here that you may read that I think at the end of this online workshop, we would love to give some feedback to NIST, and also should know what is the view of NIST on this. Particularly with the items that I have written here, I mean, we don't need to necessarily follow all these orders and all these items, just a collection of the points, which mainly also pointed out by FX in a private channel. I mean, he sent me a couple of questions that he has and want to actually warm up this discussion. That what is the first in this direction? Whether we need to focus on developing the gadgets, as most of the research in that area went, or we want to focus on a certain primitive, like just AES or any other AES box, for example, or certain nonlinear functions, and whether we need to limit or we have to define some threshold or minimum number of shares or the masking order. Shall we consider different platforms for this discussion or requirements? I mean, for hardware, for software, related to the gadget and also related to the number of shares that we have. should we consider anything about the quality of the randomness, which from my point of view is still missing, because most of these schemes that we have are based on the high quality randomness, but we are just clearly ignoring this and suppose that the good randomness is provided. I would love to know the opinion of industry in that part, because probably if they make some mask implementation in their products, they need to have some source of randomness. I mean, of course, some information are secret and cannot be revealed, but having a view of industry of how to generate the randomness and how many bits they can provide per clock cycle and what is the limitations, they are very important when we design new gadgets. Or shall we generally care about the number of randomness and say, no, randomness doesn't matter, as many as numbers that you want, we can easily provide. And the next, how do we process? I mean, what NIST wants to do in this direction? Of course, a formal or informal competition probably is not the best choice, but there we really can have some progress in that area, or if no competition planned, then in which form we need to, or NIST wants to process. Now it's open to everybody who wants to comment on this or wants to answer or start a discussion. I would probably, FX, you want to start because some of these points have been addressed, pointed out by you.
Yeah, I can try. Like the first question, focus on what? I mean, I pointed out the question, right? Not the answer for this one.
Sure,
so
sure.
I don't. What can I say? I think anyway, the first question is, do we want to focus on an algorithm or a serial of algorithm? Because then all the rest depends on that. If we want to be specific to the AES, of course, it calls for certain types of gadgets and S-boxes we will care about. If we want to be able to protect a few algorithms, it will call for different gadgets. And after this choice, I would be tempted to say we can do two things. Either for certain things that looks very useful, go for the full, like the protection of the full algorithms, but I will also go for the protection of the building blocks. I don't know to which granularity, but I think it's important in the end that designers who want to use the gadgets can decide whether they go for a serial, parallel, and so on implementations. And mixing with, as we discussed already, certain level of noise and so on. So I think flexibility, it has been mentioned already, is important, and then it calls for, it's yeah, I think it makes the design of gadgets quite relevant.
Amir, if I may, this is Apostle.
Let's go on.
Okay. Since NIST is listed a couple of times on this set of slides, I might as well take the opportunity to try to answer some of the questions that have been raised. First of all, I think it would be useful for all of us to think about primitives in the sense of an algorithm. We've talked about even the title of our documents is, or the focus of ours is to focus on the NIST-approved cryptographic primitives, in particular the block ciphers. We touched with the industry following our first workshop what would be the area of priority for the single device area, and the consensus that emerged was to focus on a block cipher because that's a widely used cryptographic primitive in hardware, and people felt that if we can provide some resolution to the problems hardware industry is facing there in terms of protecting against side channels or fault injections and things like this, that will be useful. As a byproduct of this process, we're thinking of identifying a number of gadgets that could be sort of identified and standardized by themselves as components towards building the ciphers, the larger primitives, let's say. And those gadgets could be useful not just for the AES, because currently AES is practically the only viable block cipher standard we have at NIST. But there's an ongoing parallel effort. Some of our colleagues are driving standards about lightweight cryptography, and these gadgets may be applicable there. So there's something to think about in that space. But based on the conversation that I followed for the last couple of days, and so I'd like to sort of challenge the community to think about what exactly are we going to achieve with this mission? How are we gonna you know, what is the problem we're trying to solve here? It's not clear to me. Initially, when we started this standardization effort, it was kind of obvious to us that threshold cryptography will provide added value to the industry as a means towards mitigating some of the challenges related to side channels, maybe fault injections, that sort of thing. Now, the benefit of the discussion for the last couple of days actually led me to believe that there's some sort of a disconnect between the academic view of the world and the industry view of the world. There's a block of really well-defined models and theory about them in academia, but the practice is somewhat different. Apparently, companies are using different techniques, some of them ad hoc, homegrown, some of them not publicly known, to provide protective defenses against side channels and fault injections. And these techniques are not necessarily covered by the theory. So now, if at NIST would like to develop standards that are based on theory, but at the same time, these standards have to be useful. And so we don't want to come up with paper standards that nobody's using. So the question is, if these standards are then useful, will the industry endorse them by developing products that incorporate those so that they can provide add value to the end user? So these are the big open questions that I sort of stumbled upon, having had the benefit of the discussion for the last couple of days.
Any comment?
Hi, Vince speaking.
Yeah, Nancy.
Just a second to put my camera. Okay, so I'm suppose I'm causing part of this confusion. To answer the question of opposed to what we aim, at least what I can say from my perspective, is indeed to have a kind of common solution which provides certain base theoretical for protection. And I suppose I caused this kind of disappointment in some of you, stating that formal methods or the gadgets, as we call them, the shared gates, are kind of not yet to the level that industry could accept them, or they should not be mandatory. They could be specified and as optional, but not mandatory for adoption. And why I said that is that my understanding is that one thing is what we wish, and the other is what can be achieved. And I could say that by this two-step approach, let's say, I believe we have reasons to achieve something which makes a difference. And I'm afraid that if we aim for everything together in one shot, it may result what also Apostle said that we have a standard which will be not used. And yeah, this is a choice somehow to be made.
But Wenzi, what are the limiting points? I mean, you mentioned that, for example, some gadgets are not acceptable. Let's say they are not very welcome in industry. Some gadgets, but why? Because of the latency, because of the high number of.
Let me give me an example. I think also FX said like several minutes ago. Consider a few gadgets like Ant or Source. I mean, the very basic gadgets as we have nowadays in the literature, and assume that these are the only gadgets which one can use. Assume the standard contains only few of them. This will imply that if I have to build IS protection implementation, I can build it more or less in one way only, or I have a very few flexibility to optimize to achieve certain trade-offs, as I said, for area or performance or power, because I will always will have, let's say, the S-box, which has to be implemented in 10 cycles. And I mean, I cannot do better than that. Because, for example, I cannot do a cubic function or a bit more complex function. I have no such gadgets which directly does the job. I have to obey to the AND gates and the decomposition like that. I mean, maybe it's a stupid example at the moment, but it's the first one came in my mind. And that's why I say flexibility matters. Not all, I mean, products will have the same requirements, certainly.
But Benti, I do understand what you're trying to get to, and I appreciate it. But the flip side of this question is this. Okay, you've got the flexibility, but how do you know that, how do we know that the end result that you had produced is good enough? You came up with your own set of gadgets, you combined them in a way that was useful, but you thought it was useful, but how do we know that you didn't introduce some vulnerabilities in the process? How do we test? How do we compare implementations afterwards, produced, let's say, one from your company and another from a different company that used a different set of gadgets? How do we compare the security properties of these two? How do they fold under a similar or different levels of assurance in the standard? How do we make sense of all of that in a validation program?
Okay, so certainly as I proposed, they should all satisfy the necessary conditions. At least this makes some minimum guarantees. Then the composition of them, it is difficult to answer with automated tool, or maybe it's still possible to have automated tools which just checks the properties, regardless how whether the gadget is AND gate or cubic gate or something like that. Although there is no yet such tools, at least I'm not aware. Yeah, we do it via other means like what is used now with detection of leakages, which is not exactly what NIST wants, I understand, to have fully automated end-to-end verification. But it is, as I said, one step towards something better.
May I?
Go on.
So I think, yeah, I think it would make sense to maybe have some example of gadgets which are widely used, but in order to let also not to like cut innovation, try to maybe standardize some security properties or composition properties for gadgets. ways to verify that the properties are met in practice. So of course it depends on what security property we're talking about. But for instance, for probing security, maybe robust probing security as well, we start to have a good understanding of those kind of properties and how to compose secure gadgets and how to verify secure gadgets. So I think it would make sense not to just restrict ourselves to a few listed gadgets, but let open the possibility to for designers to prove that their gadgets meet the security property. And regarding the first question, if we focus on block cipher, I think, yeah, basically we have a set of gadgets which are instrumental for AES, but as well for a lot of similar ciphers as the cipher that were submitted to the NIST lightweight competition. So probably it would make sense to be modular, not focus only on AES, but yeah, set of building blocks that can be useful for block ciphers.
Maybe answering to like this question of number of gadgets to look at. One thing with the AES is that it has many possible optimization tricks, right? I mean, you can really look at the AES box in different manners, and all of them. I mean, you can do bit slice masking. You can work in GF2 to the 8. You can do additive to multiplicative masking. It's a mine for research questions. If we go for, let's say, lightweight bit slice ciphers, there are many ones following more or less similar approaches submitted to the NIST lightweight competition. You have much less gadgets. Typically, then the basic Boolean gates are the most important ones. ARX ciphers, I would say, are another type of ciphers where you need things that are completely different. So this choice is going to really, this choice of algorithms we want to cover is going to influence quite a lot the gadgets we need. And then about what to start with, the thing, yeah, one clear question to me, which is this question of, do we want or do we consider security in the probing model or in the robust probing model as something necessary? And we had the discussion already with Vinci, like it's strictly speaking, it's not necessary if you go to lower abstraction levels. It could be that a flow in the probing model or in the robust probing model does not translate in something dramatic in the noisy leakage model or for real adversaries. But it's a risk that you take, and it's a risk that I would say it's hard to contain later on. So that's, I think, the first question, because if we say we accept these flows or we refuse these flows, it's going to change completely the way to organize or to select gadgets.
Okay, one thing that I want to say here is, or question, whether we should consider making larger gadgets than just Boolean functions, or not just two input AND gate, I mean larger nonlinear gates. Because I understand your concern, FX, that depending on how you implement, for example, the AESS box, you may end up with either many gadgets in series or many gadgets in parallel. I mean, depending on the way that this box is realized in a Boolean form. And it directly affects on the latency of the circuit, because after having the mask implementation or integrating or replacing every gate with a mask gadget, then you have a higher latency. You need register, and then you instantly increase the number of clock cycle by a factor of, let's say, 10 or even 20, right? Then whether we should consider larger gadgets, but still do we stay general? I mean, can we use these larger gadgets for other implementations or not? I mean, if we are far from the AES now, I mean, consider the other NIST lightweight primitives.
What I was saying mostly is that if we need to agree on what's the best way to mask the AES, we can start a new workshop and discuss just this question, because you have so many options that it's very difficult. if you want to protect something with a 4-bit bit slices box, you reduce the amount of questions. I have no, I mean, I do research, so it's fine to have questions. I'm happy to have all of them, but it's a very different challenge.
Okay.
Maybe can I give my 2 cents on this topic. I will want to make a step back and would like to give my view on what the Apostle said about the usefulness of the standard.
Yeah, go on.
Okay, so I think one main problem that we see in industry right now is that there exist already many products on the market with masked crypto implementations. Each vendor is claiming certain security levels without often not being able to prove it or doing some kind of in-house testing, which is unclear if, how they did the testing, or if they went through FIPS or even CC certification. So there's a big gray zone between no proofs of testing and FIPS and CC certification, where the DPA security level of the products is unclear, and it's very hard for the vendors actually to compare the products. So that's I think also what Apostle said, and I can agree on that. This is really hard. This is definitely something that I think a standard with recommendations of different target security levels will be very, very helpful, that we can say, okay, we follow those rules that are defined in the standard, and we can assure that, okay, we achieve those levels of security. Right now, this is not possible. There is no, again, if someone is claiming CC certification level implementations, then this is I would say pretty high security level, but everything that is below that, or it's very hard to say and compare how the security level really is, because there is no security bar, I would say, or different security bars. That would be very, very helpful. That's what I wanted to say.
Good. Any other comments about the gadgets?
I think the point of Michael, I want to confirm that indeed this is also observation which I share, that let's say the certification of common criteria now, let's say, focus on high-end products. Whether it's good or not, it's another story, but it has only target for these products, while for all the rest, you can think for anything which surrounds you, IoT, home, whatever. There is no criteria. Everybody can claim whatsoever he wants protection, and there is no common base or way to compare. And my hope is that these standards at least establish not only high-end bars, but also low-level bars, such that we have more widely used or way to compare all these differences. And yeah.
I'd like to make a comment as well. This is Luis with NIST. Just a note on vocabulary. So I believe that in the scope of this workshop, gadgets has been being used mostly as subcomponents of a particular circuit, like AES. In the scope of our internal reports, the NIST IR 8214 and 8214A, we typically call gadgets to subcomponents of the threshold scheme. And so in that sense, things like distributed random number generation, the kind of secret sharing that one may use, typically additive, but for example, yesterday somebody mentioned multiplicative. These components, which can be at the logical level, we often call them gadgets, in the sense that they are building blocks for threshold schemes, even if they are not building blocks of a circuit. So that's the only note I wanted to give with respect to vocabulary.
Okay, thank you, Luis. Yeah, we mainly refer to, let's say, sub-components of sub-modules in a circuit by gadget. And then we have a secure gadget, for example, secure gadget and gadget, secure OR gadget, or larger gadget, actually, was I said. Good. Shall we discuss shortly about the order of the masking, the number of shares that we should consider, or what is the view of NIST? Just wants to leave it open or make it very general, or define at let's say, a minimum for the number of shares that we should consider?
We do not have a preconceived notion about the masking order yet. I would like to sort of keep this open until we agree on the objective here for the security problem we want to address and the technology or the approach we want to take, and then figure out the rest of the details. You know, until we decide what is it that we want to do, I think we have to keep this open.
Yes, and as a complement note, we do identify the threshold numbers as one of the, what we call one of the main characterizing features of threshold schemes, as opposed to saying that's completely open at this point. And yeah, that's it.
Okay. Thomas, did you want to give a comment?
I actually wanted to ask a question, yeah. There's one thing that I've been wondering since the first presentation on Monday with respect to the validation that is envisioned by NIST, because of the methods that have been discussed mainly are things that happen during or in an early design stage, which is quite good for industry if they are designing their crypto themselves. But so it seemed in the first presentation that NIST usually wants to do something that is more at the let's say at the finished product, so more of a black box validation, right? So you provide inputs and outputs, and you check the outputs, and if they are okay, you say okay, check, you achieved this level of protection, or this cipher is doing what it's supposed to do. What we have discussed here in the workshop are mainly things during the design stage. So is that something that is actually well integratable with a NIST validation program, or are we actually solving the wrong problem at the moment? So, I mean,
this is a good.
Yeah, sorry.
This is a good question. Thank you, Thomas. Let me try to explain. So what I was describing on the slides there is the existing state of algorithm testing that we have at NIST, which is sort of driven by the so-called black box model. You have test vectors sent and the results computed and verified and so on. That works in a specific context. We know the limitations of the approach. We're not saying that that's the end goal of this particular effort. When we are talking about redesigning our testing program, we're thinking of it in a slightly more complex context, and we're extending the notion of who is going to do the test. I mentioned earlier that most government security programs are instigated in terms of these third-party testing laboratories who are designated as the only testers that can perform the test, and so they have to deal with the limitations of whether they do the end product or how do they interact with the companies to get to know their IP and all of these things. We're changing the model and saying, okay, you as a development organization, let's say your company, you have the ability to accredit yourself with NIST and establish a testing laboratory within your organization. So then you can think of doing testing throughout the product development lifecycle at the stages where it makes sense to do the testing and get the most value out of your testing process. And in that sense, we're not limiting ourselves to the black box model that you described initially, just getting you some data and you're giving some results back and that's it. We're willing to accept all sorts of evidence that makes the case for asserting a specific security level and the corresponding documentation. We would be expecting that you would maintain a good housekeeping so that you know what kind of test, what kind of tools you use, what kind of results you got, what kind of products those results are from, and things like this, so that later if we send some auditors to verify what you did, you can actually reproduce these tests. And so that's really the open testing problem that we're sort of approaching differently now. And we're saying, okay, for us it's acceptable to do pre-silicon testing as well, if that provides value and we can gain assurance from it. It doesn't have to be the end product, just the end product.
So then these methods would actually be helpful. But how much do we then still need a final validation test for the end product, because of addressing aspects like noise, right? So you just before said that, okay, we want to maybe decide on or specify the number of shares as a security metric, for example, right? So but then we also heard that there is it depends strongly on noise. So would there be a requirement that you have to ensure with a number of shares that you also provide a certain level of noise so that you actually get a acceptable protection in the end?
I mean, I would say so, yes. But sort of like what the chip manufacturers do, when they produce silicon, they don't test every wafer, but they do statistical sample, they pick some end products, they measure their properties, and they make a judgment over the entire production line. And so I would assume that once you have done all the testing during the design phases of the product, and you've come up with a mask, then you go to foundry, you produce the final chip, you have to do some kind of a final product test to characterize it properly and report it in the same manner as I described before. So you have a consistent testing and reporting story to maintain in your company as archives, such that if somebody came and asked you what kind of testing did you do, you can show the record and be able to reproduce parts of it per auditor instruction.
All right, thanks. That clarifies a lot.
Let's ask the audience if there is any question. Please raise your hand or write in the chat or unmute yourself. Okay, it seems there is no reaction from the audience. Okay, from the panelists, if there is any other question or any discussion that you want to start?
Yeah, maybe. About the question of the masking order, I think, yeah, it would make sense to first define what we are trying to reach exactly, of course. And this is related to the question of which attack, which adversary we consider. And I think that's something we should maybe discuss in priority.
Yes.
So there have already been some discussion whether to consider like the most powerful attack, like multivariate attacks, template attacks, horizontal attacks, these kind of attacks. The thing is, against those attacks, it's maybe what we know to do well today, like probing security, is kind of insufficient against those type of attacks. So I think that's an important point to address. So maybe to give my 2 cents on this question. So I think that today we know well how to reach probing security for a lot of algorithms with a lot of different gadgets that we know well how to compose. and we can achieve it to arbitrary orders. So that's, I think, and I think it makes sense in practice to consider probing security against a type of attacks which are not the strongest attack possible, right? But you might consider an adversary which is not so powerful, that cannot have access to a control device, that cannot profile the leakage, and that will maybe try some more elementary attacks like standard DPA or higher order DPA. And against this kind of adversary, probing security is relevant. Then if we consider a very powerful adversary that can have access to a copy device and have a lot of computing power to perform leakage characterization, and will apply the latest multivariate attacks in the literature, for instance, using deep learning techniques, these kind of things, then probably probing security is insufficient, and we should consider noisy leakage security or things like the random probing model. But in those models, the secure constructions and tools are less mature that for probing security, and probably it would be a bit early to try to standardize. Maybe we could find some relevant criteria, but construction, I think it might be a bit early. So yeah, that's my 2 cents.
Thank you.
Yeah, I would agree with that. And one point is, I think, like, again, maybe it's certainly you can always improve the model, but I think if you take the models that we have, the biggest challenge is to reach security and tight security as we go towards the more practical model. This is what we still don't know. So that's one thing. And the other is if we stick with probing security, we probably know more or less how to do that, and we can do that without defining a platform. But obviously, probing security is let's say, necessary condition or close to necessary condition. This can be discussed, but it's certainly not sufficient. And then all the other things like these horizontal attacks, they relate to noise. Noise, it means you need to define a platform. And then it comes back to I think, Vincent's first talk, saying maybe if we want to analyze something there, we could at least specify 2-3 platforms that we believe relevant, that are open, that everybody can try, so that we can claim something for the noise level and the security on those particular devices, which is not going to be ASICs. So it still remains a lot of things that we cannot completely do. That's fine, but maybe once you have a working FPGA prototype, it's easier to turn this into something useful for industry. I don't know, like it's obvious that the challenge of saying something in the noisy leakage model is huge. And relates also to this evaluation question, right? We just don't, there's no super regular way to test, to agree about the security level as we have for probing security.
So, but then one question is, do we want to be platform specific? I mean, to be platform dependent?
No, obviously we don't want to. So, but I don't know, I guess for probing, any claim in the probing model is platform independent. Any claim on the noisy leakage model becomes platform dependent. So I don't see, either it's platform dependent or it's kind of assumption dependent. You say, okay, this thing is going to work if you guarantee this level of noise, and it's up to you to do that.
Yeah.
But how could we avoid being platform dependent for something as specific as the noise distribution?
I think we can avoid that with yeah, some noise parameter, like the
in
the noisy model.
You can get closer with random probing security or whatever, but in the end, like when you're really in the noisy leakage security model, then it's also analog. Like the question of the correlation between the time samples, for example, depending on whether this is verified or not. Like all these evaluations that we do will be different, right? Because correlated noise is not independent noise. And this correlation, it's even more than the device, it's the precise setup that you use. That's for Amir, I guess. Huh? But I would say at some point things are difficult to model super accurately because it's physics.
Yeah, yeah, maybe I don't see like a very strong technological issue here, I think, but probably we are not yet there. We're not as mature. There is still research to be done in this area, but yeah.
The question is also how precise that has to be, right? So I mean, if in other engineering disciplines, you usually have some margin of error as well, right? So maybe you can approximate the amount of noise that you get from a device. And yes, of course, it depends on the measurement setup and so on. But obviously, if you have FX in your talk, you said basically, yeah, certain class of device, low-end microcontroller, you can in software you can do whatever you want. You will not get security if you have a capable or a good measurement setup, let's say it that way, right? So, and then, okay, it's done deal, right? So obviously with such a device, masking order, I don't know, 32 is not gonna do any good. But if you are in a scenario where you at least somehow can approximate the amount of noise you have, and maybe again, right? So measurement, depending on the measurement setup, it's a little more, or a little less. But at least you know a rough order of magnitude of noise, and then you can say maybe with a masking order 4 or something, I'm fine, right? So maybe you don't have to go the additional step. You have some numeric values for noise, for example, some limits that you need to guarantee, and then you can say, okay, this limit together with security in the probing model, for example, and then I know I'm secure up to this number of measurements or something. Right? So maybe that's a viable.
Yeah, that's right. But this is a little bit like saying, okay, we take this platform, let's say this FPGA, we hope it's reasonably representative. Let's see what you can do with this noise level. And this defines more or less what you have to achieve to reach this security level. I still think it's easier to have one actual platform that you can measure to really argue about the final security level.
So I agree, it's helpful to have a like exemplary platform, but then you could define some standard way to evaluate the amount of noise or the order of magnitude of the noise, and then still be general and let the door open to next generation devices. Because what you do on the current platforms to evaluate the amount of noise, that's some techniques that you can use for any device, right?
Yeah.
Yeah, I think that the security order alone may not be the best metric, so maybe we should combine it by some type of noise estimations as well. But I also see an issue when we, especially for lightweight, but if you want to apply those standardized gadgets to lightweight ciphers, then the noise level might be really, really low on certain platforms, so that the number, the security order, the recommended security order needs to be really, really high to achieve, I would say, like an equally distributed DPA security level throughout the statistical moment landscape. Then this doesn't become lightweight anymore, right?
Okay.
Okay, Vinci again speaking. Coming to the fact that assuming now we have somehow a way to measure the noise correctly, or during the evaluation process. And we have chosen order somehow, which is also verifiable. Then comes to the question of the claim how many traces somehow you are protecting on the device you are going to certify, and then the error, as I think, has been mentioned also. Maybe returning to the slide UFX presented. I don't know to what extent, I mean, this is representative or just a suggestion, but I'm just looking now on it. It says that if we have hardware with noise, then one share, probably this means unshared implementation. You have like 1,000 traces, guarantee, security. And with 3 shares, you have like 1 million. So there is no clear, let's say, first order boundary. And to what extent this is tight bound, upper bound, lower bound. I mean, probably this has to be well or better specified, let's say.
Yeah, completely. So the slide is only informative to show that it's noise plus order. And if you have more noise, it's easier. Where you're completely right is if you want to be complete, everything can be bounded, I think, or many things can be bounded. But if you really want to have bound and take all risks into account, the thing will not be tight, and you will be in the end overly conservative in the number of shares and the amount of noise. And I think this is in the end kind of just risk management. Right? There are effects like low order effects that with the amount of measurements that we make as evaluators, we are not able to see, that could pop up later on. If we really want to consider this risk and increase the number of shares and the noise accordingly, you probably pay more than what you need. So either you use these theoretical bounds, and that's one option, or you really go to practical attacks and you see how far it is. Sometimes, like Mathieu mentioned the case of software, I think practical attacks will be not so far from the bounds. For hardware, you have more things that can happen. I don't know exactly, but yeah. One thing that's not in the table, obviously, is the amount of risk or how conservative you want to go with the evaluation.
Okay. Would like to use the rest of the time to ask NIST how they would like to proceed in this direction. Do they have any certain plan? As it said, whether it should end up with a kind of a competition or no, if not, in which form?
Okay. Well, how we would like to proceed? First of all, we are determined to have an open and transparent process. That's extremely important to us to make sure that everybody is included and what we do is transparent to the public. We don't make decisions in the dark. In a domain like cryptography, this is extremely important if we're developing standards that will be widely accepted. And we'd obviously like to be grounded on merit. Whatever we choose has to have appropriate merit behind it. And so in that sense, we have to agree with you as a community what is the right approach to driving this process forward. If, as Louis was saying, when we talk about gadgets in the threshold cryptography sense, there are some gadgets that have been around for a while, like secret sharing, Shamir, and all the others. There's probably no need to compete on them. We can agree as a community that that's a component that makes sense, you know. But then how do we approach it with respect to the gadgets that you guys talk about at the lower level? That's something that we all have to agree. I think the fundamental principles of transparency and openness necessitate that we agree on the rules for the competition or non-competition amongst ourselves, and then we'll act accordingly.
Okay.
Yep. I can compliment a bit. So I second what Apostle said. And with respect to the question on how to proceed, so one of the things we identify in the current NIST-IR is a sequence of envisioned phases. And really the immediate challenge that we have in front of us before even considering things, whether there's going to be a competition or something different, is the challenge of devising criteria. Basically criteria for considering threshold schemes, and only after a phase of criteria would we have a phase that we call a phase of calling for contributions. Now, calling for contributions, we foresee that this may mean various things. For example, a request for contributions could even just be contributions for reference definitions that would be useful as definitions for gadgets. If when devising criteria for some aspect, we know very well the kind of thing that we want, and we also know that there are many ways of achieving it, then possibly one could consider that a call for contributions could be indeed a call for concrete proposals on how to achieve something, so that later on something would be selected. But even with respect to that, as also mentioned in the first presentation, there are nuances of what a competition can be. So one nuance, which maybe could be what we actually call competition, is something where, okay, there's a set of possibilities, there's a set of proposals, and one will be selected. But then there are also ways in which there may be several proposals, and then the process of evaluating those proposals could lead to some merge of ideas or some adjustments. But in any case, I would say that in front of us right now, the phase of devising criteria is a challenge on its own, and it's a relevant challenge to consider before even wondering whether we're going to have a competition or not. And I think as we move towards devising criteria, there are already contributions that would be helpful, and in particular, the goal of this workshop of coming up with some deliverable that will already certainly be helpful for us. I would say that, for example, having contribution from the community in terms of enumerating what are the attacks that definitely we should consider, what are maybe what is possibly an enumeration of security properties that should be considered. Naturally, security properties are often measured with respect to attacks, but for example, certain properties at the algorithmic level, like we've been hearing on uniformity, non-completeness. I would say that with respect to these ones, having receiving from the community reference definitions for these properties, and even description of aspects to consider. For example, as we've heard in a previous comment, certain things that are platform dependent or other things that are platform independent. If those are aspects that we need to consider during the phase of criteria, all of those would be very useful. And I feel that is really the challenge we have in front of us right now, receiving enough feedback to devise good criteria. And I would say, as we receive that feedback, certainly we will have some time to pose that back to the community and ask feedback to the enlarged community whether they think that the feedback we just received is good, and basically give time for people to reply back and agree and or disagree.
Okay, thank you. But in which form you want to have the feedback? I mean, currently we have this workshop, of course, there will be some feedback, but then in future, how do you want this communication channel between, let's say, academia, industry, and also NIST?
Well, that's a good question, and we have set up a number of mailing lists related to this effort, and we invite everyone who hasn't joined us to join us, and those who have, we are going to engage with you and reflect on this workshop, and as Louis was saying, proceed with identifying the criteria. All the input that we got during this panel alone is quite valuable, and we hope to continue to develop these ideas, to specify them further so that we can actually come up with the standards that we want.
Okay. Good.
And I think it is reasonable to imagine that based on the workshop alone and on possible feedback that we receive after the workshop, we can internally also try to distinguish between the things that for us look as consensual at this point versus the ones that maybe we don't understand and we'd like to pose questions about them. And I think naturally we will have a phase where we will pose those conclusions to the community and basically ask and basically say we would welcome any feedback that the community has with respect to our interpretation of what we've heard so far. And so there's kind of an iterative process here, which hopefully will be a converging process. Time will tell.
Okay, thank you.
Actually, if I may add, the first step would be releasing the notes that we were doing during the workshop. And we'll also try to add up at the end some kind of short summary, how we see it, and then I'll distribute it to everybody. If you have other visions or if you want to add anything, this will be possible in this document. So
that would be great.
That would be probably the first thing to do after the workshop.
Good. Sveta, do you want to take over? I think the panel is now terminated and based on the schedule, if I'm not mistaken.
Yes. Unfortunately, we didn't have time to discuss the randomness problem. Yesterday also, we didn't have time. Today also. I don't know if anybody has any quick remarks on this. What quality of
problem
need?
It's a problem that we postponed for many years already anyway.
Yes, yeah, nobody likes really to tackle it very much.
I think we have 10 minutes, Svetla, if I just initiate something with the industry partners that they are available here. May I?
Yeah, we can. I mean, we have the time until 5. We don't have really anything. Okay. I don't have anything prepared to finalize.
Okay.
Yeah.
I think Matteo is here. Mike is here also. Venci.
Hi.
Can you tell anything about the difficulty that you have if you want to generate random numbers, random values, fresh mask or whatever, the mask inside the circuit?
Okay. I could say from hardware perspective, although I'm assuming that from software it's a completely different world. So when you design your chip and you put your masking, of course, you have to provide certain randomness. You may need like 50 bits or 100 bits or whatever amount per cycle. And you're take into account and you dedicate specific pseudo-random generator just for that, which is you can share with other protected implementation. You have not only IS probably there, you have other algorithms as well, but it's more or less dedicated for masking. So it does not satisfy the criteria of NIST for super random generator and so on, but it's performant sufficient for the task you want to. And that said, if I need to generate 1,000, this could be a problem per second. Yeah, amounts like the ones I mentioned are not something which prevents you to do it.
You mean 50 bits per clock cycle you can generate easily?
Yeah.
Yeah, but of course, this is the proprietary information from NXP. Probably we are not able to ask that. How do you generate these 50 bit per clock cycles?
Okay.
And then whether they are, each one is independently uniform or not. I mean, they are very, very important questions, right?
Okay, I unfortunately cannot go in gory details to explain how random they are, but they're good enough for the purpose.
Okay.
Yeah, I agree what Bente said. I think you cannot compare the RNGs that are used to generate masks or random values for masking purposes is different as for the NIST RNGs to generate cryptographically strong keys, for example. So this is different. And a good question that I want to throw in here is also like, should we bound the security level or entropy level actually, or the security level of the entropy source? Should we match that with the targeted DPA security level? And that would also help actually reducing the required resources. So it's actually, I mean, as you can imagine, the more bits you want to generate, the larger the circuit will be, and also the more power will be consumed. I think it's more a power issue than an area problem here. But I think as you asked before, like generating 50 bits per cycle. I mean, it's definitely possible. It's a question to the customer what their power budget is and area budget, usually generating those mask bits is not the highest priority or the biggest problem that we see right now, but it's definitely something that helps if you have an efficient entropy source to make the whole design more efficient. But yeah.
Can you, for example, comment on the area that you need for 50 bits per clock cycle? I mean, compare it to the area of the one AES that you have. Of course, I don't want to get equivalence numbers, right? Is it a size as large as the AES, or double size of the AES, of half of the AES? How large it is to generate 15 random bits?
Well, I don't have the exact numbers in mind, but I mean, we just published a paper also where we report those numbers.
Okay, good.
It's taking a certain amount of area and power, but it's not the majority part or the major part of the circuit. It is large. I cannot remember exactly. Maybe 5 to 10% of the total area, maybe. But again, it really depends also on which countermeasure you implemented, on which AES implementation you consider, if it's, how many SBOSs you have in parallel and all this stuff. So, but it's, I would just refer to the paper if you're interested.
Thank you.
I can add to this kind of similar percentage, let's say. Approximately, I also don't remember the exact numbers, but it's by far less than the total size of IS. And the more important point here is not area, but indeed the power, since I think we presented even for the NIST workshop in Washington, the power figures for Prince protection. And you can see when you use randomness for refreshing all the time, the power consumption grows quite a lot. Meaning, if I have a big random number generator, I refresh a lot, all this budget explodes, and it's constrained.
Matthew, do you want to say something?
Yes, I might say a word on the software perspective. So basically, if you want to implement a crypto algorithm with some masking and let's say smart card or an IoT device, you hope that the device is equipped with a true random number generator that you will use to generate the masks. Then the issue might be if this TRNG is slow, you might be limited in the number of masks that you can generate. So that's compromise between security and performance to be done. Then if you don't have a TRNG, it's more challenging. I mean, if you can always generate your mask with the PRNG, but if you do that in software, then it's a bit of a chicken and egg problem because you should protect this PRNG against side channel attack as well. So yeah, I think that's some issues that have been carefully ignored from in the scientific literature, and that now we start to investigate those questions. There have been a recent paper about considering minimizing the randomness requirement for masking schemes and still getting some security proofs at last Eurocrypt. And yeah, so yeah, from the software perspective, you just hope that you have a TRNG. But it's usually the case if you're considering device which is made for secure implementation, right? You need some kind of assumption and to have a minimal hardware security features so that you can build software security on top of this secure hardware.
Thank you. I just feel that I just feel that NIST in future with respect to this, let's say masking and so on. I mean, threshold implementation of threshold security and single device should probably comment on how to generate the randomness on the chip, because currently I see that in industry everybody just takes some scheme and of course keeps it proprietary. I mean, completely hidden and secret. Nobody knows how the randomness are generated, and then one day after reverse engineer it, some flows can be explored, yeah, I mean, or exploited. And I just think that NIST should play a role here in this direction and have some suggestions how to generate the randomness on the fly. Yeah.
Amir, if I may, a comment about the RNGs. So a main motivation for us to look at threshold schemes at a high level is to avoid single points of failure. I guess a question for the community is, to which extent are the RNGs used in masking schemes a single point of failure, in the sense that if they are compromised in a particular way, do we completely lose the properties that we were assuming that we were getting with respect to, let's say, computation of AES? And as a follow-up question to that, and assuming that indeed a compromise of RNG would be something very bad, what kind of threshold approaches can we consider for the implementation of the RNG in itself? And it's within this setting that we consider RNGs a gadget in threshold schemes. So I guess a kind of a natural question would be, in pair with the threshold properties that we want to achieve, let's say for execution of AES, should we have some kind of distributed RNG scheme such that we can say, okay, it's a kind of 3 out of 3 RNG generation, maybe everything is XORed, or maybe you concatenate everything and then hash, although hash would probably be yet another subcircuit. But should we consider distributed RNGs, or do we have any setting of implementation of primitives where it's actually not important to have a distributed RNG? Possibly a distinct question would also be, as somebody mentioned, maybe you, Amir, I forget now who commented, that often these RNGs in the circuits are not the full-blown RNG generation that NIST requires, a la SP 890 series. Is it reasonable to imagine that maybe in a threshold single device setting, we don't need to have that kind of RNG generation, but in compensation, we should have some kind of threshold RNG generation, where each of the RNGs does not need to be as good as the full-blown RNG requested by NIST.
Can I just hop in for just a moment, Luis? So, hi, Carrie McKay. I work at NIST, and we are currently working on a new draft of 90C with different constructions for the RNGs. So if you have any ideas on this, we would love to hear it. So right now we've got some deterministic constructions where they are, they only have access to entropy when they're first instantiated and they have no ability to recede. We have deterministic ones that can be receded because they have intermittent access to an entropy source. And then we have some true random number generator constructions, or in our lingo, the non-deterministic random bit generators. So we'll hopefully be coming out with that soon, but if you have anything else that you would like us to consider, please just let us know about it.
Very good, thank you.
Yeah, I can try to answer the question about what happens to security guarantees. One thing that's clear is that all the proofs in the threshold probing model, they assume perfect uniform randomness. So if you have an imperfect generator, formally these guarantees disappear. If we wanted to deal with that, we need a model that is qualitative and that allows us to quantify the bias in the random number generator. Really formally doing that, I don't think we have the tool right now. It's a nice question. Heuristically, I think that's what Mike said. Essentially, at least you hope that the bias in your RNG is such that distinguishing this bias requires more sample than just targeting the implementation directly. But this is completely informal. And then for solutions, I think you always have two options. Either you work on the RNG side and you try to make this one secure via either you share it itself, or you try to do randomness extraction and things like that, or you try to design gadgets that tolerate a certain amount or a certain deviation of the randomness. And I don't think much has been done in this direction, and maybe it's going to be more expensive too.
Thank you, FX, for this comment. If I may, a follow-up question on this. So you mentioned something related to how the security proofs are done, and you are basically saying if there's problems with randomness, then we may have certain problems with security proofs. But in a different setting, are there? I really don't know. Are there works that are there practical attacks that exploit exactly the randomness? Let's say, at least at the logical level, are there attacks where basically the attacker is able to replace whatever flux of random bits by a stream of zeros, and therefore be able to attack and extract the key from a circuit?
Oh yes, they are. Like if you take all the papers that are based on low entropy masking schemes, where the idea is to reduce the amount of mask, not take them uniformly, but trying to make them matching the leakage function. Remove their assumption. Essentially, all those work where the leakage function is perfectly linear. Take these masking schemes with a nonlinear leakage function, and they are deadly broken, first order. And take one value out of 256 that never pops up. It's also directly a very practical attack, which is essentially what you have with the zero problem of multiplicative masking schemes. On the other hand, but that's not exactly what we do at the moment. If we were doing operations in very large fields, which is typically, if you have this theoretical paper by Jemberski and Faust on inner product masking, where the inner product masking takes place in a 128-bit field, then these biases are directly not important. But for all the things that we discussed today, I think they are attacks for strong biases.
If I can add something to that, it's Lauren from COSIC. So I think, Luis, your question was kind of like, is there a practical attack? And I think the example you gave was more like a fault attack, because you said like the random bits are replaced by zeros. And so that's a different, those are two different things, right? Does the RNG need protection against side channel attacks or against fault attacks? So for fault attacks, yes, definitely, because there has been a practical attack, I think, in software where the attacker targeted kind of like the communication from the RNG to the masking scheme, and in that way he was basically able to disable the masking, right? If you can disable the randomness. So there is indeed an example of that.
Yeah, thank you.
Okay, it seems it's a good target for new research to be done in this area, but unfortunately we have no more time to discuss now. But I'm happy we have tackled this question as well, because this is always kind of put in the apart from everything, not really in the focus of our research. Okay, any other burning questions that someone wants to say before we finish? Anything from NIST that you still want to add?
I guess I would just say thank you very much.
Thank you.
Go ahead, Apostle. Maybe you're gonna comment.
I was going to say the same, Svetla, thank you to you, to the whole team at KU Leuven for organizing and hosting the event. I think we are off to a really good start. I found, in particular, the discussion of the last panel very encouraging. But we also recognize that there's a lot of work to be done to complete our mission of creating useful standards in this space. And so I would encourage everyone to please work with us in the coming weeks and months to specify the criteria, to figure out the models, to figure out the problems we want to solve, and the exact way of how we're going to manage this standardization project in order to achieve the results that we want. Thank you.
Thank you. And I also would like to add that this was just warming up for a Lawrence workshop, hopefully, which will happen in February if everything goes well with the coronavirus, and hopefully physically as much as possible. Of course, here we were very, very focused on a very specific question, how we standardize threshold on single threshold cryptography on single device, while the Lawrence workshop will be much more wider, and we can discuss anything that is research relevant in our community. But I don't dare to make any plans yet before we see how the winter and the autumn and the winter comes. And once we are close to that, we will contact you again, and hopefully we can continue working. It was obvious that there's a lot of things to be discussed and a lot of things that we need to align with. And before we finished, I repeat again, we have had a wonderful team of young people from COSIC who did tremendous job these 3 days to collect all the notes. I just want to mention their names because I'm really, really grateful to them. Thanks a lot, Danilo, Simen, Lauren, Pong, Zenda, and Victor for doing a very difficult job these 3 days and for collecting everything we have said. And we will produce a more structured document out of them, and I'll send it to all of you. We'll give you a couple of days to put your notes, suggestions, corrections that you find necessary, and we will deliver this to NIST as input from this workshop, and hopefully they can do something with it. For the rest, thank you everybody. Thank you all the speakers, all the panelists. Thanks for spending all this time and devoting it to this workshop, and we'll finish almost on time the 3rd day. Thanks a lot again.
Thank you. Bye.
Bye. Bye, everybody.